Hello everyone, welcome to lecture 53 of the online course on Introduction to Microwave and Optical Metamaterials. Today's lecture will be on tunable metamaterials. Here is the lecture outline. So, we will first discuss about the need for tunability in metamaterials. We will highlight the limitations of conventional metamaterials, and then we will briefly introduce this concept of tunable metamaterials and take up some examples of magnetically tunable dielectric metamaterials in the form of ferrite wire composite structure, or ferrite metamaterial filter and some ferrite dielectric composite structure. So, let us first see why tunability is required in metamaterials. So, we have understood that the electromagnetic response of a metamaterial basically depend on the specific structure of their unit cells, and you can design different unit cells for metamaterials operating at different frequencies. Okay, so we have seen the applications like in radio frequency domain. You can be making metamaterials for absorbing, so they can work as meta absorbers or antennas. In the terahertz domain, you can make sensors and detectors. In optics, we have seen you can make perfect lens, invisibility cloaks, and also achieve super resolution imaging. So, what is the problem? The problem here is that once fabricated, these fixed structures will operate within their specified frequency range. You cannot tune it, right? So, if you want the structure to operate at a different frequency range, slightly different frequency range, you need to redesign the structure and go through the process all over again. So, changing the frequency will require a redesign, and that is where the cost will also come in picture, right? So, you have to do the process again. So, what is the solution? So, you can think of making these metamaterials dynamically tunable via some external fields that will act as stimuli, okay, without causing any physical or structural change to the metamaterials. So, that brings the concept of tunable metamaterials, and we will first look into tunable dielectric metamaterials. Okay, these are basically sensitive to external stimuli such as magnetic field, electric field, temperature and strain. And tunability in the visible and near infrared range is also critical for advanced optical applications. So, as you understand that they enable real-time control of the electromagnetic characteristics, and their key applications involve wireless communication systems, radar, smart antennas, microwave devices, okay, for this kind of metamaterials. In the case of optical, you will understand that there are different tunable optical devices that can be made from this metamaterials, which are dynamically tunable. Now, let us categorize these tunable metamaterials. The category will be decided based on their tuning methods. Okay. So, let us first consider magnetically tunable metamaterials that can adjust permeability and permittivity using external magnetic fields. The advantages here will be like you can achieve wide tuning range and faster response speed. Then you can also think of electrically tunable metamaterials. So, here the properties of the unit cells can be changed by changing the bias voltage, okay. And then you will have thermally tunable metamaterials. So, here you are basically using the external stimulus of temperature, right. So, you basically have the scope of leveraging the temperature dependent dielectric constant changes, right. So, you can stack VO2 over TiO2, this kind of multi-layers, and using the metal insulator phase transition in VO2, which is a very common phenomena, the dispersion can be tuned, okay, from elliptic to hyperbolic dispersion, which you have discussed already in this course. So, that can help you to gain that tunability. Next, you can also use strain stress for tuning the metamaterials. So, here the electromagnetic properties will be altered by mechanical deformation, right. So, these are ideal for variable and flexible electronic systems. So among this, let us focus on magnetically tunable metamaterials because of their wider tuning range and faster response speed, right. So this is what we will be looking right now, magnetically tunable dielectric metamaterials. So magnetically tunable metamaterials, again you can understand that these are metamaterials or engineered structures which allow modification of their electromagnetic properties under the influence of an external magnetic field. So the key tunable properties obviously are the permittivity and permeability, right. So the tunability is basically enabled by the interaction between dielectric resonators and the magnetic materials within the metamaterial structure. So when you vary the external magnetic field, it is possible to dynamically control the resonance frequencies as well as other electromagnetic characteristics like local field distribution in this kind of a structure. So this capability basically makes them ideal for dynamic and reconfigurable devices in advanced electromagnetic applications. Ferrite is a gyromagnetic medium that exhibits ferromagnetic resonance under an external magnetic field. So this particular resonance enables realization of negative magnetic permeability within a given frequency range. So tunable frequency ranges where you can have this negative permeability can be tuned by tuning the applied external magnetic field. So when you bring ferrite materials into your metamaterial design, okay, so that is basically enabling you to develop tunable electromagnetic devices such as negative refraction metamaterials, metamaterial based antennas, metamaterial based band pass filters and band stop filters, right. So now let us look into one particular application, okay, of this kind of structure. So here you can see a ferrite based metamaterial using yttrium iron garnet ferrite rods with copper wires, okay, in this particular structure, okay. So this is designed to achieve magnetically tunable negative refraction. So you can carefully see this particular structure. It consists of YIG rods, copper wires, okay, on either side of PCB substrate, okay, and then you have external magnetic field, that is H naught, okay, that is applied along the long axis of the ferrite, okay. So this is how the wave will be propagating through this metamaterial. So this is the wave direction, and you will have this is x and this is z axis. So wave is propagating along y axis, that is marked with wave vector k. So magnetic field of the incoming wave will be along x and the electric field will be along z. So this is the schematic. So you can see this is a periodic structure made of YIG rod, and on the back side you have copper wires on two sides of the PCB, okay. So this is the metamaterial, and when you obtain the transmission spectrum for this metamaterial over a frequency range of 8 to 12 gigahertz. So this is the magnitude of S21 that tells you about the transmission coefficient or the transmittance, okay. So you here the same thing is obtained for different applied magnetic field strength. So the solid black one is for 1600 OE. So OE is basically Oersted, that is another unit of magnetic field strength. So if you want to correlate with Tesla, so 1 OE is basically equal to 12.566 millitesla, okay. So that way you can correlate between Oersted and Tesla. So here you can see the magnetic field has been increased from 1600 Oersted to 2300 Oersted, and that has allowed the center frequency to shift from 8.2 to around 10.7 gigahertz, okay. and the tuning response speed basically reaches 3.5 gigahertz per kilo oersted. Okay. So, that is how you can tune the bandpass property of this particular structure, right. Now, this structure enables dynamic, continuous and reversible magnetic tunability across a broad frequency range that you can see here. Okay. Now, the term reversible basically here refers to the ability of the structure to return to its original electromagnetic state when the external magnetic field is removed or it is reduced, right. So, the reversible behavior here basically means that the magnetically tuned electromagnetic property such as negative refraction or the transmission window that you are seeing here, they can be both increased or restored depending on the applied magnetic field. So, that basically enables dynamic and repeatable control over the performance of the metamaterial. So, you can say that this metamaterial structure exhibits broadband magnetic tunability, right. So, the best thing is the operating frequency can be easily adjusted by changing the external magnetic field without altering anything in the structure. This can be further extended to achieve dual band property. You can introduce another set of ferrite rods of different sizes into the structure. So, when you have YIG rods of varying sizes placed on both sides of the printed circuit board, it is not shown here, but if you repeat the same exercise that you change the external magnetic field H naught from 1900 oersted to 2300 oersted, you will see that you will get basically two pass bands now. So, the first pass band can be moved from 9.1 gigahertz to 10.2 gigahertz when you change the magnetic field from 1900 to 2300 oersted, and the second pass band can also be shifted from 9.5 to 10.6 gigahertz for this magnetic field change. So, this kind of result confirms that you have magnetically tunable dual band response from the structure. Okay. So, these are ferromagnetic resonance or also called FMR that you see in ferrites. So, this FMR or ferromagnetic resonance occurs when ferrite material interacts with magnetic field of an electromagnetic wave, and this basically leads to a change in the material's effective permeability, okay, which is causing the change. So, let us see how it happens. So, under an applied magnetic field H naught, you can write down the effective permeability in this particular form. So, you can write mu effective as a function of omega will be 1 minus f omega square mp divided by omega square minus omega square mp minus I gamma omega omega. So, here gamma omega is basically given by this omega square by omega r plus omega m, okay, plus omega r plus omega m times alpha. So, alpha is the damping coefficient of ferromagnetic precision, okay, and then you have this f, this constant f, which is nothing but omega m by omega r. So, omega r is the resonance frequency, omega m is nothing but the characteristic frequency of the ferrite, that is given as 4 pi capital Ms gamma. This gamma is the gyromagnetic ratio, okay, and Ms is nothing but the saturation magnetization, right. So, from this you can find out the ferromagnetic resonance frequency, which is omega r, that can be expressed as gamma square root of H naught, that is the applied magnetic field, plus Nx minus Nz, okay. So, these are basically the demagnetization factor along a particular direction, okay. So, Nx minus Nz times 4 pi Ms into H naught plus Ny minus Nz 4 pi Ms. So, H naught, as I mentioned, is the external magnetic field. Nx, Ny and Nz are basically the demagnetization factors in the x, y and z direction respectively. So, based on these equations that you see here 1, 2 and 3, so you can understand that the magnetic permeability of ferrite is strongly dependent on resonance frequency, right. So, here you can actually see the real part. So, here you can actually see in this figure. So, the permeability and the permittivity. So, here the real part of the permeability and real part of the permittivity over this given frequency range is plotted, okay, for different applied magnetic field 1800, 2000, 2200 and 2400 Oersted. Okay. So, you can actually see that where you are getting negative permeability and here you are getting negative permittivity in all the cases. Okay. So, these are basically for the combination of the ferrite rods with copper wires, okay, at different passband frequencies, right. So, we have also discussed about the dual resonance effect. So, when there are two different sizes in ferrite rod, you basically start getting two negative permeability regions near their ferromagnetic resonance frequencies, and that allows formation of two left-handed passbands when it is combined with metal wire array, which is providing negative permittivity, right. So, you can see that this ferrite metal wire combined structure, okay, is typically a structure that gives you left hand material configuration, right. So, this structure basically supports low loss magnetically tunable characteristics, and the best thing is it is very simple to construct. Now, let us look into a structure of ferrite metamaterial filter. Okay. So, this is a magnetically tunable band pass filter using YIG ferrite arrays. Okay. So, the design overview tells us that you are going to design a band pass filter using two YIG ferrite arrays. So, you can see this particular diagram. Okay. So, you can see that two different color rods are shown. These are basically two different ferrite rods with different 4 pi ms magnetization property, and then you have Teflon substrate in which the entire thing is embedded. Okay. So, the gap between the rods are considered to be D, and A is the periodicity. So, this is where the microwave enters and this is where it exits from. This is the overall height of the structure, and this is the direction of the external magnetic field that is being applied. Okay. So, as you understand that these arrays will have different saturation magnetization ms, okay, and their corresponding transmission characteristics are plotted here. So, what is important here to note that you are getting basically two dips, and in between you are getting a flat band, and this is the band pass filter characteristics, and this is possible because of using two different ferrite rods with different saturation magnetization. Now, saturation magnetization is a fundamental magnetic property of ferromagnetic materials such as YIG, yttrium, iron, garnet, that basically tells you the maximum magnetization of a material that can achieve when fully magnetized by an external magnetic field. So, here you can see the values of the saturation magnetization of the two YIG rods. One is 1200 OE and another is 1950 OE. Okay. All other parameters are basically taken as identical. So, you can obtain the ferromagnetic resonance behavior according to this equation: omega r equals gamma square root of h naught plus nx minus nz times 4 pi ms, the whole thing times h naught plus ny minus nz 4 pi ms, right. So, here you will see that the ferromagnetic resonance frequency depends both on the external magnetic field h naught as well as the saturation magnetization of the material, right, and the resonance frequency basically increases with higher saturation magnetization. So, here you can see that in this case, because you have two YIG arrays which have two different saturation magnetization, you basically have two different resonance ferromagnetic resonance frequencies, and this two ferromagnetic resonance frequencies basically give you two distinct stop bands, as you can see here. So a pass band is basically formed. So we are just talking about this solid black line, which corresponds to the case of 2400 Oersted. Okay, fine. So these two dips basically tells you about the two stop bands, and there is a pass band in between. And the best thing here is that you can see that the pass band has the insertion loss of only minus 2 dB. Okay, so it's a very good performance for the filter, and it's pretty flat as well. Okay, so the negative permeability here can be generated by the ferromagnetic resonance. You can take this equation, okay, which you have seen earlier, omega effective, mu effective as a function of omega can be written as 1 minus f omega square mp divided by omega square minus omega square mp minus I gamma omega omega. Okay. So the central frequency of this pass band, that is this one, can be dynamically tuned by changing the magnetic field strength. So if you change it to 2600, you will see you are getting two red dips, this red dashed lines. So the pass band is actually shifted here. If you further increase the external magnetic field to 2800, you are looking at the blue dotted line. So the pass band basically shifts over here, right. So now let us look into the opposite kind of filter, that is band stop filter based on this ferrite based metamaterials. Okay, so you can also design band stop filter using YIG ferrite rods, but this time you can go with different sizes of rod. Okay, so one is big, one is small, as you can see here, and remaining structure looks pretty much similar as the previous one. Okay, so you are again here just making two ferrite arrays, but this time they are different in size. So what you see, you can obtain the transmission characteristics, okay, transmission spectrum, and it shows a stop band. Okay, and you can see the stop band has a bandwidth of around 500 megahertz at minus 3 dB, and insertion loss for this is typically minus 1.5 dB. So the solid black line shows you the band stop filter at 2200 Oersted applied magnetic field. If you change it to 2400, it moves to this red one, so this becomes the new filter. At 2600, the blue dotted one shows you the filter characteristics. So you can actually shift from somewhere say 9.2 the center frequency to somewhere around 10.5. Okay, so that way you can change the central frequency of the stop band and increase it with the increasing external magnetic field. So this basically confirms the structure's magnetically tunable characteristics. Now let us also look into some more ferrite dielectric composite structure that allows dual band magnetically tunable extraordinary transmission. So based on the Bethe theory, electromagnetic waves cannot pass through metal plates with subwavelength holes. Okay? Now a structure that can transmit waves through such holes will be very important for microwave and optical devices. So a proposed solution to this kind of phenomena would be to design a dual band magnetically tunable structure. So this structure basically enables extraordinary transmission through these subwavelength holes. So here you can see that subwavelength hole, and you can see this is the schematic diagram of the dual band magnetically tunable filter, and this is the transmission characteristics. Okay, there are two bands basically, right. So what is the structure here? The structure basically consists of two pairs of dielectric cubes and ferrite rods, so one on the other side as well. They are basically placed symmetrically around both sides of the subwavelength hole. So same structure is on the other side as well, right. So you will see that you have basically a dielectric cube that you see here, and then you have a ferrite rod. Now these two material basically have different characteristics, and that is why you get the first passed band that is coming from the Mi resonance of these dielectric cubes. Okay, and then you have the second pass band, that is basically coming from the ferromagnetic resonance of the ferrite rods. Now, if you think of tunability, the pass band that is originating from the Me resonance is not affected by external magnetic field, because that is coming from dielectric structure. But the pass band that is coming from the ferromagnetic resonance is coming from a ferrite material, so it can be dynamically tuned by changing the external magnetic field. So, H is changed from 1000 to 1500 to 2000 Oersted, and you can see this is how the second pass band is changing, right. So, what few important observations here is that when the magnetic field, external magnetic field is 2000 Oersted, okay. So, the peak value of the two transmission bands will be somewhere close to minus 1.3 dB, that is for the Me case, and this one is around minus 2 dB, that is coming from the ferromagnetic resonance. Now, here are some simulated electric energy distribution profile in the XY plane that is calculated at two different frequencies, okay. So, this allows us to see the electromagnetic wave transmission through the subwavelength hole. So, this is that subwavelength hole, and this is the structure that you have put dielectric cube and ferrite rod on either side, okay. So, you can see that when you do not put anything, okay, so no EM wave is basically getting transmitted through this metallic plate. So, this is the metal plate with the subwavelength hole, there is no transmission at all, and this is due to the Bethe theory, right. And when you put the ferrite rods and dielectric cubes, you will see that even at zero magnetic field, okay, you will see the transmission is occurring at 10.76 gigahertz, and that basically corresponds to the Me resonance of the dielectric cubes. So, there is transmission here. So, this is the phenomena of extraordinary transmission, right. And at 1500 Oersted, you see that the ferromagnetic resonance will take place. So, it will occur at 11.31 gigahertz frequency. So, you are basically getting again extraordinary transmission, but this time at a different frequency because of the applied magnetic field, and this is happening at 11.31 gigahertz. So, in a sense you are basically able to tune the extraordinary transmission frequency also by changing the applied magnetic field. So, what you observe from here is that this ferrite dielectric metamaterial composite structure basically enables dual band operation. It is coming from the Me resonance supported by the dielectric cubes and ferromagnetic resonance supported by the ferrite rods, which is also seen here. This is the Me resonance, these are from the ferromagnetic resonance of the ferrite rods. And using these two resonances, you can achieve extraordinary transmission that is basically getting tuned from 10.76 gigahertz to 11.31 gigahertz, right. So, you can actually use this concept for making modulators, isolators, etc. So, with that we conclude this lecture. So, we will discuss about electrically tunable metamaterials in the next lecture. If you have got any query regarding this lecture, drop an email to this email address mentioning the course title and the lecture number on the subject line. Thank you.